Hello, good afternoon. This is first revision lecture for design of steel structures. And in this lecture, first lecture, we will just see unit 4 and unit 4, whatever syllabus we have, whatever clauses we have to use, and which type of problems are expected in unit number 4. That discussions we will go for revision lecture 1 in revision, and after 1 we are going to solve different types of problems. So now if you will go to my YouTube channel, that is Civil Engineers Technical Hub, then you will come across different playlist, and in this you have to go through steel structure playlist. And in this steel structures playlist, you have to refer to videos which are related with laterally supported beams. So you can see I have mentioned over there. So first video will give you theory part and mainly focus. And second video you will be with different types of problems. So here we are going to solve this, but for practice, you can refer these two videos which are related with your unit number 4. Now unit number 4, this you relates with your flexural member. Now flexural means bending. And these members, when we will say bending, mainly or most of the times we are with shear force. Means flexural member we have to design for bending, or we have to design for bending and shear force. IS 800 2007, this is for your design of steel structure, or we can say structural design 1. You can read it. Design of members subjected to bending. When they are going to say bending, means your load should be transferred to the axis. Loads transfers to the axis. Sorry, transverse to the axis. So loads transverse to the axis. And when you have loads transfers to the axis, then we are going to say members are flexural member. Flexural members. Now we can have member pure bending, or we can have shear plus bending. Now if we have beam like this, so reactions are same because it is symmetrical. If I will say as L by 3, L by 3 and L by 3. And if we will draw bending moment diagram, so we have this as PL by 3 constant and PL by 3, and we are going to say this portion, this is pure bending. Pure bending. And if you will go through this portion, because now you can say why this is pure bending, because x to the power 0 in bending moment diagram, and that means we do not have anything in SFD. If I will draw SFD over here, so we have P, do not have any load, then go P below, no load, and then we have down, then we have P. So this is my SFD. So as we do not have anything in this L by 3 portion, so automatically you will see x to the power 0 in bending portion. And this is pure bending. If we will say this portion, then we have this as shear force plus bending moment. Bending moment. Now, if we will go to any diagram, if I will draw a bending moment diagram for a UDL throughout this span, then we are in this fashion. Now, in this, we have this portion which is middle L by 3, we can say. So from both side L by 6, L by 6. Then we have, this is bending predominant. Predominant. Now if we will go to this portion which is after this, then we have this as combination of shear force and bending moment. So now I can say this. So both are considerable, SF and BM. SF and BM. And if we will go to the last portion, this portion where you have shear force predominant. In this portion, you have shear force predominant. So we have this region and we are interested in this. This is bending moment predominant and shear force and bending moment considerable. Means both are considerable in the design. Only shear force predominant. This we are not going to study in this flexural member. Because then that member goes to shear actually, and we do not have in our syllabus that is designed for shear. So now we will go with this. So we can have this section 8, and this is for flexural member. And here it was clearly mentioned, member subjected to predominant bending shall have adequate design strength to resist bending moment, shear force, and concentrated forces imposed upon and their combination. Means section 8, these are for bending moment predominant. So I can say this portion. And if we will go to section 9, which is combined effect, and in that section 9, we are going to be this portion. Now we will go with effective span. Then what is effective span? Shall be taken as distance between center of support. So I am just making these brackets. Now if we will go to the next, then they have mentioned here that factorial design moment. So this M, this is due to loading. Try to understand difference between MD and M. So this is due to loading. And MD, you can see, you can read here, design bending strength. This is property of the section. Property of section, or you can say capacity of section. Capacity of section. And our capacity of section, which is MD, should be always greater than M, which is due to external loads. So M should be less than or equal to MD, or I can say MD should be greater than or equal to M. Critical we have MD is equal to M. This will be critical. Then we can have laterally supported beam. So that we have seen types according to your SF and BM. Now this laterally supported and unsupported, this goes to compression flange. Compression flange will decide my beam is laterally supported or my beam is laterally unsupported. Now how it will decide? So you can read over here. A beam may be assumed to be adequately supported at the supports, provided the compression flange has full restraint and nominal torsional restraint at the support supplied by web cleats, partial depth end plates, fin plates, or with adjacent spans. So these whatever may mentioned over here, these are related with supports. But full lateral restraint to compression flange may be provided. Means my compression flange, if laterally restrained, then I will say it as laterally supported beam. If my compression flange not laterally restrained, then I will say it as laterally unsupported beam. Laterally unsupported. So that unsupported means not supported, and laterally supported or restrained means laterally supported. What does it mean? So laterally supported means lateral deformation is prevented. Lateral deformation is prevented. And if not supported, means not restrained. What does it mean if we will say a beam and if this beam get laterally means perpendicular to this along the flange, if we will get deformation perpendicular to this, then we are going to say that is laterally unsupported. But if you restrain, how you will restrain? We can provide slab on it. If you remember, in trusses, we are going to provide sheets on purlin. And J-bolts we are going to use to connect these sheets to purlin, so it becomes laterally supported. In beams, we are going to provide slab, and for their connection, we are going to provide shear connector, or shear connector we can say, or you can say connectors. And as therefore they will make bond between the slab and beam, and therefore they are again laterally supported. If nothing is on this flange of the beam, compression flange of the beam, then we are going to say laterally unsupported. Compression flange is going to decide your beam is laterally restrained, laterally supported, or laterally unrestrained, not laterally restrained, or laterally unsupported. Now again we have two clauses you can see over here. First, when the factorial design shear force does not exceed 0.6D, this is again most important one. So your V, shear force, VU I can say, does not exceed means less than or equal to 0.6 VD. VD is design shear strength. Design shear strength. And if my VU, ultimate shear force, is less than 0.6 VD, then we are going to say bending predominant. And when bending predominant, we are going to use this value of MD by using this formula, beta B ZP Fy upon gamma. And this value shall be less than 1.2 ZE Fy upon gamma m. Now, from where this 1.2 comes, if we will go to IS 800, that is where we have sections, I sections, that table is there. And in that table, you will see ZP by ZE, which is our plastic section modulus to elastic section modulus as shape factor. And this value you can say ranges from 1.1 to 1.2, maximum 0.2, and therefore this is taken as 1.2 ZE. So if you will put this 1.2 ZE, then you are going to get this value as ZP Fy upon gamma m. So likewise, this value comes 1.2 over here. Beta B we have 1 if our section is plastic or compact. And this we are going to see from table 2, page number 18. And from there, we have to decide this section. Section is plastic, compact, or semi-compact. If section is semi-compact, then my formula becomes this formula. This is for your, or I can write both formula. So we have MD is equal to ZPFY upon gamma MO. This is for plastic and compact. Plastic and compact. And if we will go for semi-compact, then we have MD is equal to ZEFY upon gamma MO. This is for semi-compact. So that you have to see. Now gamma MO partial safety factor, we have to go to table 4 and 5 where we have partial safety factor for loads and materials. And now if your VU is greater than 0.6 VD, then my beam is analyze, or I can say better design for combined loading, because here both are predominant, and for this we have to go to section 9. And from section 9 you can see MDV is defined in 9.2 because section 9 this is for combined loading, and from there we have to find value of MDV, which will be considered as design bending strength. And that design bending strength is not for pure flexural member, and that we have for combined effect. So this is actually overall what is your unit number 4. And now in next lecture we will see what problems we have to solve for this. That we will see in next revision lecture. So now we will stop here only. Thank you.